Test, test. Test, test. There we go. Boom, boom. Who's in the chat? You're watching the replay right now and you're just staring at me. I'm waiting to get some viewers here live. What's up, River? My day's going well. How's your day going so far? Thanks for watching live. Ya. Got the notes posted. Rough. Why is it rough? Anybody else in the chat right now? Anybody else watching? Able to connect. Why? Oh, dang. So strenuous. It's a strenuous day. I don't know if I'd call that rough. Sounds like something you want to do. My iPad want to connect? There we go. For sure. That does sound like a lot of work. But it'll be nice when it's done, right? Well, should I go ahead and start? Anybody else out there? Or is it just River and I? Alright, well, I'm going to go ahead and start. Nonetheless, I'll have a replay available. Can you ask a calculus question? I can give it a shot real quick, yeah. Before I start my notes, yeah, I can give your question a shot. Can't guarantee my expertise, but I have taken calculus. A couple years of calculus in college. Limit problem, eh? Well, the top is bobbing up and down, right? Doesn't matter. Sign goes back and forth between 1 and -1. When I look at that, I've got sine of x over 2x squared minus 4x. This right here is never going to be, it's bobbing up and down between 1 and -1. But this denominator is just getting bigger and bigger and bigger, right? So it doesn't really matter what this is. The fact that this is getting big, small over big, means that it's getting really close to 0. And that's how I do that. All right, you got to think. Oh, as x gets close to 0, my bad. I was thinking infinity. Well, sine of 0 is 0. Oh, but the denominator would be 0 as well. So when we get 0 over 0, you can do L'Hopital's method. You know what L'Hopital is? So you take the derivative of the top and the derivative of the bottom. So you'd get cosine of x over 4x squared minus 4. So this would be 1 over -4. I think that works. Does that make sense, ancient origin? All right. I don't know where ancient origins went. Okay, cool. Sweet. So that was L'Hopital's method. All right. So starting now, here's the replay. Hello, replay folks. Hello, people watching the live stream. We are doing geometry right here at the start. We're doing lesson 2.2. We're talking angle pair relationships. Okay? Angle pair relationships. So there's some relationships that we need to know and understand that help us solve problems involving angles. The first one is vertical angles. And you can think of vertical angles as angles that are on opposite sides of one another. So 1 and 3 here are vertical angles, and 4 and 2 are vertical angles. So you have this intersection of lines. The vertical angles are the ones that are opposite of one another, right? 1 and 2 are side by side. The word for that is adjacent. Okay, to be next to one another means adjacent. But vertical angles are on opposite sides of one another. So there's that. And so are 4 and 2. There's that word adjacent. So a linear pair, think about that phrasing, linear pair. Pair meaning 2, linear meaning line. So it's 2 angles that make a line. So this is a straight line, and these 2 angles combined make this straight line. So what does that mean? If these 2 angles are making a straight line, that means that 5 and 6 add to 180 degrees. They are a linear pair. That one's a pretty straightforward fact. I like that one a lot. And vertical angles are equal. I think I forgot to say that. I said what vertical angles are, but I forgot to say that vertical angles are equal, which is pretty obvious visually speaking, right? 1 and 3 look just about the same size. 4 and 2 look just about the same size. Supplementary and complementary are two big buzzwords that we like and we need to learn. So where a linear pair is specifically two angles that are touching, right? They are adjacent. They're literally right next to each other. Supplementary angles don't have to be next to one another, but supplementary and linear pair are essentially saying the same thing. The two angles add to 180 degrees, but they don't have to be side by side. They can be side by side, the word for that being adjacent, but they don't have to be side by side, aka adjacent. They can be separate, right? I can have this angle over here on the page and this angle over here on the page, and as long as the two, why is it doing that? As long as the two add together to be 180, 50 and 130, we can call them supplementary. And the same logic can be said about complementary, except that they add to 90. So as we see examples and as we remind ourselves of these definitions over and over, we'll start to get used to them. I think linear pair and vertical angles are the most instantaneous, that just make sense, right? I don't think I need to tell you that these two things add to 180. I think we all just kind of see that, right? We're like, oh, straight line, 180, right? 360 means all the way around. Flat line is 180. And visually speaking, 1 and 3 look like the same size, 2 and 4 look like the same size, and they are. You can't always trust your eyes, but you can on some level. So let's just have these quick examples here. So 5 and 4, they are adjacent, right? Because they share a side and they're making a straight line. What do we call that? A linear pair. But since they add to 180, they're also supplementary. So I can actually use both words for that, right? Either or would be correct. 5 and 3. So the key thing about vertical angles is that they're made by intersecting lines. So this line and this line are intersecting one another. And 5 and 3 are on opposite sides of that intersection. So we call them vertical angles. 2 and 3. So 2 and 3 are right here and right here. How big is this angle? Not really sure. 2 and 3, though, do share a side. I think the best word and the only word that we can use for that, kind of a tricky one, is simply adjacent. There isn't anything special about them besides the fact that they share a side. So we can just simply call them adjacent to one another. I'll answer these questions in just a sec. Let's keep going here. Decide if the statement is always, sometimes, or never true for the picture above. The measure of angle 5 is blank equal to measure 3. Well, what did we say about 5 and 3? They are vertical angles. And the one thing that we know to be true about vertical angles is that they are equal to one another. So that's always true. There's never a situation where vertical angles aren't equal to one another. That's what makes them vertical, is the fact that they're equal. Measure of angle 4 and 3. So we didn't talk about 4 and 3 in the previous problem, but 4 and 3 are adjacent, and these two angles together make a straight line. So we call that a linear pair. And linear pairs, what do we know about them? They add up to 180. This is saying that they're equal. I think it's pretty obvious that 4 and 3 aren't equal. But could they be equal? Theoretically, yes. They are sometimes equal. Only once, when they're both 90, right? 90 and 90 make 180. That's the only situation. But technically, it's not never, right? I know visually speaking, I don't know why I drew a question mark. I know visually speaking, right? I'll draw a little eyeball. Visually speaking, they do look different, but they hypothetically could both be 90, right? The measure of angle 5, 1, and 2 added together is equal to 180. 5, let me use a different color. Red. 5, 1, and 2, yeah, they're making a straight line. And what's the measurement of a straight line? 180 degrees. So that's always going to be 180. There's never a moment where a straight line isn't 180, so we're going to say always. So over here, which angle relationships must always share a vertex? So looking here, which ones must share a vertex? Another way of asking that question is which ones are touching, basically. Right? If they aren't touching, then there's no way that they're sharing a vertex. Okay, so River's got a question there. Let me finish that thought and then I'll totally answer your question. So which ones are touching? Well, these two are out, right? They could be touching, right? That's a situation where I would say sometimes. They're sometimes touching, but this says always, okay? So supplementary angles could be touching, but they don't have to, right? So neither of these are the correct answer here. Linear pair and vertical angles are touching. Are they sharing a vertex? The vertex is where it's sprouting out from. Yes, 6 and 5 are both sprouting out from the same point. That point is called the vertex. So linear pairs always share a vertex. And look here. This angle is sprouting out from this point, and this angle is sprouting out from the same point. Yes, they share a vertex, so vertical angles as well. So let's go over that logic of sometimes always. So let me just erase all my other thoughts here and just start from the beginning. So here's 4 and 3. Yeah, that's what we're talking about. Well, 4 and 3, what do we know about 4 and 3? They're a linear pair, meaning they add to 180. Now, in this drawing, I understand that 3 and 4 don't look equal, okay? But we have to suspend our disbelief. Drawing not drawn to scale, okay? Technically speaking, is it possible that 4 and 3 could be the same size? Right? If two angles add to 180, is there a moment in time where they're both the same? Right? They could be 30 and 150. They could be 40 and 140, right? Adds to 180, adds to 180. Well, they could be 90 and 90. So it's not always equal, but sometimes they are when they're both 90. So that's why I said sometimes. And 5, 1, and 2. In this drawing, 5, 1, and 2, all three of those angles make a straight line. A straight line is always 180 degrees. There's no doubt about that, right? I can't draw a straight line and it not be 180 degrees. So with that being said, always. Which angle relationships must always be adjacent? The only one that I have is linear pair. Vertical angles only share the vertex. They don't share any sides, right? When I draw these two angles, there's angle 1 and there's angle 3. They don't share sides. They're not next to each other. They're opposite. Only these guys share a side. All right. Tell whether the angles are vertical angles, a linear pair, or neither. Okay, well, let's do it. 8 and 5. There's intersecting lines, and they're on opposite sides, vertical angles. If this were real class, I'd have you guys do these on your own, but I'm just going to give away the answers. If you want to pause right here, if you're watching the replay, I understand that if you're watching live, you can't pause me. But if you're watching the replay, I would encourage you to pause here and try to answer these on your printed out notes or on a scrap sheet of paper or something. 5 and 4, they're right next to each other, so they're adjacent. Adjacent doesn't immediately mean linear pair, but because of the fact that they make a straight line, it is a linear pair. 4 and 9, well, that's if looking at this intersection, 8 and 5 is one set of vertical angles, and 4 and 9 is the other set. So vertical. I often do a little angle symbol to say angle, right? Because I'm too lazy to write the word angle 20,000 times. So I do vertical apostrophe S. So like angles. You see what I'm saying? So instead of writing the word angle, I write the angle symbol. 6 and 7, they make a straight line. Another linear pair. I'm going to write LP. 1 and 3. So if you paused and did this, you might have been tempted to write linear pair because you're like, oh, I see a straight line. But 1 and 3 don't make a straight line. 1, 2, and 3 make a straight line. 1 and 3 are just two random angles. Neither. Okay, so the way I like to do these problems, like in class and doing notes, is, and something that you should always do first, is identify the relationship first. Okay? For any problem, right? Even down here, identify the relationship first. On any problems like this with angles, we want to know what is the relationship first and foremost, because we can't solve for anything if we don't know the relationship. So when I look at these two side-by-side angles making a straight line, I immediately say linear pair. When I look at these two angles opposite of one another, I immediately think vertical. I see a right angle, that's 90 degrees. Do we remember the word from up above? Complementary. Because these two angles make a 90-degree angle. They don't make 180, they make a 90. So that's complementary. These two angles side by side forming a straight line, a linear pair. These side by side angles making a right angle, they're complementary. And I don't particularly see anything for that one. We'll leave that one for the end. I'm not trying to go quick and like lose you. I'm trying to go quick and like imply how easy it is to identify the relationship. Right? You kind of have you have three options. In for the most part, I shouldn't say always, but for the most part, we have three options. Either the two angles are going to add to 90, the two angles are going to add to 180, or the two angles are just going to be equal to one another. Right? It's got to be one or the other for the most part. So these two angles are a linear pair, so therefore they add to 180. So I just real quick subtract the 98 and I get, I don't want to mess that up in my head, 180 minus 98 is 82. These are vertical angles. I immediately, real quick, know that that's just 64 degrees. I think a lot of this we probably know how to do subconsciously, even without like me having to teach you all that much. You're like, okay, if this is 90 and this one's 58, well, 58 plus something has got to equal 90, right? I think we all naturally are doing that in our head, whether you write it down like I do or whether you're just kind of thinking it through in your brain. You're still thinking essentially the same thought. Okay, thanks for the poggers. So I subtract the 58 and I get 32 degrees. This one's the same as that one. This one's the same as that one. I'm glad you love math, Claffy memes. Um, I'm trying not to make this super long, right? Whether we're watching it live or watching the replay, I'm not trying to suck up all our time. So those are like the same examples. This one real quick is 135, and this one real quick is 56. If you want to just confirm, you know how to do it. But what about this one? How many degrees are we looking at here? This is 299, and then there's these things. There's a relationship that I haven't explicitly said, but it's something that we should know, is that going all the way around is 360. Okay? So going all the way around is 360 degrees. So what I'm saying is B plus. So what am I saying here? What am I writing? I'm saying, all right, if I combine all three of these angles, and by combine I mean add 299 and the 28 and the B, that should give me a whole 360. So 299 and 28 adds to 327, and then subtract the 327, and B is equal to 33 degrees. These things over here were just a reminder of our definitions. So real quick, I'm just going to say they add to 180, add to 90, and this just means next to one another. Very simple and easy, I would agree. And these are just as easy, except we're solving for x. So I don't want you to get intimidated by the fact that there's no number, right? And there's x's. The same thoughts should be going through our head. So I'm gonna skip immediately to these guys. I'll pause on this for a second because I'm kind of looking at similar problems, right? There's just no numbers. But again, identify the relationship. Okay, I see a straight line. What does that mean? We have linear pairs, or in this case, you could call it a linear triplet, right? I know that all three angles add to 180. So it's not exactly a pair, but more of a triplet. And what does that mean? That means that ABC plus CBD plus DBE equals 180. That's what that means. So I'm doing something very similar to like what I was writing up here, right? I said this thing plus this thing should equal 180. Now, granted, I'm going to have to do algebra now, but writing the equation was just as straightforward, right? If you're not as skilled at algebra, I mean, that just comes with practice. But writing the equation is like the most important part, I think. So 11x and 5x make 16x. Negative 2 and negative 4 make negative 6 plus 90. Well, these two things can combine. So 90 minus 6 is 84. Subtract the 84. Whoops, what am I doing? $16x equals what? 96 Divide by 16, I get 6. If you gotta use a calculator for a couple of those, that's fine. I did it in my head. River, since you are watching with me and using the good old chat, let me know if there was a step on the algebra you want help with. Classy memes, if you're still with me, just give me another poggers. Or you can ask a question too. So x equals 6. Perfect. Again, I look at this and I'm like, well, I have another straight line. I'm literally using the exact same logic to write this equation. So I'll do my color situation again. ABC plus CBD should equal 180. So 8x and 6x make 14x. 9 and 17 make 26. Subtract the 26. I get 154. Right? Yeah. Divide the 14. I get 11. I didn't write divided by 14, but I said it. Got another one. X equals 11. Dope. Thirsty. I have water in this thing. I have a little bit. Can you even read my chart? That's utter nonsense. Still seems simple. I agree, River. Let's do it one more time. What do we have here? So this one, it's simple to River, but in case you're watching and you're like, okay, what am I going to do here? You might look at this and you might be like, well, there's a linear pair, right? There is, but I want you to take a look at this. 6y plus 8 plus x plus 42 equals 180. That is true. However, what do I do with two variables in a problem? The answer is I don't know, right? You can't have two variables in an equation. It just doesn't work out. You can't do anything with that, right? That's weird and confusing. And I'm not just saying that. I'm not pretending to be dumb and I'm like, oh, well, there's some advanced way. Literally, if you only have one equation with two variables, you can't solve it. But I can see that, wait a minute, I have vertical angles as well on this page. And those two vertical angles are equal. And that is my equation this time around. The two vertical angles are equal. And there's only one variable. And that is something I can handle. And I can do the exact same thing with 52 and x plus 42. So x plus 42 is equal to 52. Subtract the 42. I'm running out of room, so I'm not going to write that. That's just 10. So x equals 10 and y equals 20. Awesome. All right, so to go back up to the top here, to just knock out those final examples, and then we're done. This wasn't too long at all. It instead of giving you a picture, it just gives you a statement, which is honestly but probably easier, right? Because you don't have to look at the picture and decide what it is. It's literally telling you that these two things are complementary. And what does that mean? They add to 90 degrees. They add to 90 degrees. So add the two things together and you should get 90 degrees. So x and x give me 2x. 11 and negative 15 give me negative 4. Add the 4. I've got 94. Divide the 2. I'm running out of room. I get 47. So this problem is essentially telling you which equation to write. It says, yo, add them and get 90, because that's what complementary means. And this problem screaming at me, yo, add them and get 180, because that's what supplementary means. So 5x and 17x, what is that? 22x. Add the 2 over. 22x equals 182. What is that? 6? What is that? Divide by 22. Oh, it's a fraction. Whatever. Okay. So I get 182 over 22, which they're both divisible by 2, and I get 91 over 11. Which we've had some problems where it says enter your answer as a decimal rounded to the nearest tenths. So I would do 91 divided by 11 and get 8.3. I know, it was the only one that didn't come out to a whole number. But I didn't add 5 and 7 wrong, did I? 17 plus 5 is 22. Yeah, it just didn't come out to a whole number. That's fine. River, if you're still with me, you got any questions for me, man? Classy memes for life? Perfect. How's classy, though? Classy memes, you still with me? I'm going to make an announcement for out. So we're done, Geo. In case you're watching the replay and you're like, is he going to say anymore? That's it. I'm going to make an announcement for Algebra 2. Just wrapped up geometry and I'm starting the notes soon. Come watch. Make sure to watch live or the replay before class. Links. Twitch. My light on. And save. All right. Let me pull up Algebra 2's. Boom! Get the jams while we wait a couple minutes. That's good to hear. can be repetitive. I mean, there's so many small skills that get used in every problem, you know? Like, I mean, to go back to what we were looking at, right? Like, it's not new to do algebra, right? But yet it was new to identify these relationships, right? And some people aren't as visual and they don't quite see what we're seeing, but eventually they get the hang of it. But yeah, then you turn around and do all this, and it's like, well, I've done that before, and I've done it 1,000 times, and that's true. We have. But then, we use this plus something with segments plus something with something else, and then it's like, it's repetitive, but you gotta remember this, and you gotta remember that, and you gotta remember that, and that's where people start to struggle. Is they're like, oh, which thing am I doing? What do I need to look for? Do we have any Algebra 2 people in here? Have we gotten any more viewers? Not the same amount of viewers. All good. If any viewers are trickling in from Algebra 2, we'll start here in a minute or two. Just gonna wait to see if anyone pops in from that announcement that I made. I'll be starting about 1 or 2 minutes. So what is there to say about math right now as we kill a little bit of time? Math is just such a great topic, It's just one of my favorite things about math is that it just works, Math just always works. There's always a right answer for math for the most part. I mean, there's new discoveries in math, constantly. And they have to prove that it's the right answer, and sometimes they're wrong. But our math class, there's always a right answer. There's never a wrong. There's never a possibility where, well, we don't know if that's the right answer or not. It always works out. It's a puzzle that you can always find the solution to, and you can always check your answer. That's one of my favorite things, that you can always check your answer. Whether that's with a calculator or by graphing, there's some other method to confirm the work that you just did, That's one of my favorite things, is that you can confirm your answer. Now, it takes knowledge to confirm your answer, right? But I'm hoping a little more people have trickled in for Algebra 2. I'm just kind of talking to myself right now as I'm waiting for a couple more viewers, and then we're going to start. Anyone new has joined, feel free to message in the chat. Let me know you're here. I should have something on the screen that says message hi if you're here, or something like that. Just so I know people have shown up. Well, I think it's probably best just to get started. It is already almost 4:30. It's 4:20 right now, actually. So, we are solving more quadratic equations. All right. Well, okay. So, hello, Algebra 2 stream. How's it going? We are starting lesson 2.3. To jog our memory from the previous lesson, just to get us back in the flow of things, right? We were given equations in this form here, right? Where we're given some equation and we have to solve it. And it might be something like x squared plus 6x plus 8 equals 0. Let's jog our memory as to how we were doing that. We were doing b over 2 plus u times b over 2 minus u equals c. So that turns out to be, in this problem, what is b? B is 6. What is c? C is 8. So 6 over 2 is 3 plus u times 3 minus u equals 8. And we multiplied these two things together, and we saw that every time we multiplied something like this, b over 2, let's just call it b over 2 plus u and b over 2 minus u, what's going to happen is no matter the numbers, these two middle terms always canceled out. I know I'm somewhat rushing, but I'm just trying to refresh our memory. We're always going to have a plus something u and a minus something u. And those somethings are always the same and cancel out. And we just end up with 3 times 3, which is 9, minus u squared equals 8. And then and so then I would move my u over, u squared, subtract the 8, I get a 1. Take the square root, u equals 1. And what was the point of that? Well, I could now say 3 plus 1 equals 4, and 3 minus 1 equals 2, because that's what these are, right? And 4 and 2 means I can write the following. X plus 4 times x plus 2 equals 0. This right here, which came from these two numbers, is called factored form. And x equals -4 and -2. What up, Cube? That's actually a new way of factoring that I recently learned. You probably were taught something different when you were in high school. So there's the jog of our memory, right? Hopefully that came flooding back a little bit and you're like, okay, I can do that. You can do that. So let's take a look at these. My teacher voice. My explaining voice turned off. I have an explaining voice and a non-explaining voice. So I look at this. If I were to use that same method, I don't have a middle term here, and you might be looking at that struggling like, well, what is b then? Well, b is 0. There's no 0. Okay, so 0 divided by 2. Again, what is it? B over 2 plus u, b over 2 minus u equals -25. Or equals c, sorry, which is -25. So I have 0 plus u, 0 minus u equals -25. So I end up with 0 times 0, which is 0. I just end up with -u squared. How easy is that? Equals -25. The negatives canceled, so u equals 5. So I end up with 0 plus 5 and 0 minus 5. So I end up with x plus 5 times x minus 5 equals 0. So what are my two solutions? X equals negative 5 and positive 5. I don't need to mansplain inflection. Well, I don't like it being called a teacher voice. It's my explaining voice. Teacher voice implies that, like, I'm doing it for the children. No, I would do it for anyone. So, you see how easy that was, right? Because there was no middle term. Remind you of something? I don't want to have to do this every time, right? I These can be solved quicker. These really can. These can be solved quicker. And I don't want to have to do this every time, right? And so I want us to see something that's going to happen. I want us to see something because it happens every single time, right? There's no middle term, right? Where else did I already mention that? Down here when I was doing my example problem. There's no middle term. Why is that? Because we have 3 plus u, 3 minus u. We have the same thing. One's a plus, one's a minus. Right? I cannot stress that enough. Like, I'll literally sit here and do 3 examples to prove my point. Right? 4x minus 3 and 4x plus 3. So I end up with 16x squared minus 12x plus 12x and minus 9. The middle term cancels. I just end up with 16x squared minus 9. I'll do it again. Let's say I have 5x 2 and 5x minus 2. 25x squared, 10x, negative 10x minus 4. So it's just 5x squared, which gives me 25x squared, and 2 squared, which gets me my negative 4. Right? This thing squared, this thing squared. No middle term. Should I even read that essay that you just wrote? One more time. In my teacher voice, 3x minus 4, 3x plus 4. The middle term cancels out. Okay? So, how do I go backwards? Because that's the point. How do I go backwards? How do I go back into my factored form? Because what we're saying here is that 3x minus 4 and 3x plus 4 equals 9x squared minus 16. They're the same. Well, let me give you, let's say, 16x squared minus 4. What does that go into? Look, this is the square root of that, and negative 4 is the square root of that. All right? So this becomes 4x minus 2 times 4x plus 2. Do you see the pattern yet? 9x squared minus 25. What does that factor into? 3x minus 5, 3x plus 5. Boom, it's instant. 36x squared minus 49. Getting a little bit bigger, but if you know your perfect squares, 6x minus 7, 6x plus 7. Boom. Right? This is the same thing as this. This is the same thing as this. This is the same thing as this. I hope by just doing a million in a row, you're seeing the pattern. The buzzword for this is a difference of squares. Difference meaning subtraction, squares meaning perfect squares. So I'm subtracting perfect squares. 16 and 9, 25 and 4, 36 and 49. I'm subtracting perfect squares. So I look at this one and instantly know it factors into 4x minus 2, 4x plus 2. So my solutions are, what do we recall? What do we do with these factors? We set them equal to 0. And every time I get a positive and negative solution, right? Positive 1/2, negative 1/2. I look at this and I instantly know, because it's a difference of perfect squares, 4 and 81, I instantly know that that factors into 2x minus 9, 2x plus 9 equals 0. And I can set each of my factors equal to 0, and I get, I get positive 9/2 and negative 9/2. Beautiful. Okay. So, what are we looking at here? Well, we're missing the C value, are we not? We're missing a C value. There's something else that's just easier, right? This method works every time. And maybe I should do one using that method. Let's do one using that method, and then I'll go, well, look at this pattern that shows up. So let's do one normal here, normal in quotes. So b over 2, 9/2 plus u, 9/2 minus u equals c, which is 0, because there's no c term. So 81/4 minus u squared equals 0. Well, so interestingly enough, I'm just going to turn around and, so I just squared something, and now I'm just going to turn around and take the square root. You see that? So I have 9/4, or 9/2, sorry, equals u. So I squared it, 9/2 times 9/2, and then turned around and took the square root of it again. And what are my two guys here? 9/2 plus 9/2 and 9/2 minus 9/2. So I end up with 18/2, which is just 9, and 0. So it turns into x plus 0 times x plus 9 equals 0. So my two solutions are 0 equals, small to big, right? So this gives me negative 9. And this one gives me 0. I want to write this a little differently here. It's x times x plus 9, right? I don't need to write plus 0, right? Plus 0 means nothing. Plus 0 means nothing. I will answer your question in a second. So plus 0 means nothing in this situation. X times x plus 9. So I'm just going to write x. All right? So what's happening here that we can see here? Well, I want you to take a look. This I could, let me backtrack here. I could simply distribute this and put it back together, right? X times x is x squared, and x times 9 is 9x. Boom, right? I'm back where I started. So is there something that I can see, visually speaking, just looking at this, that I could undo distribution, right? Could I undo something, right? These both had an x. So I can yank that x out and have x times x plus 9. And I say, hey, there's a solution of 0, and hey, there's a solution of negative 9. So when I look at this guy, visually speaking, what do they share that I can sort of rip out, right? What can I remove from this? Well, they both have x, and 16 and 4 are both divisible by 4. So I can say 4x times 4x minus 1. Do you see how I can now turn around and put this back together? 4x times 4x is 16x squared, and 4x times negative 1 is negative 4x. So there's a word for this, right? I'm going to use the buzzwords here. So this is a difference of squares to remind you of that buzzword. What we just pulled out here is called the GCF, greatest common factor. So when I look at these guys, what's the greatest amount that they have in common? They both have a 4 in common, greatest common factor, and they both have an x in common, greatest common factor, 4x. So my solutions, set your factors equal to 0. That's something we do every time. I don't care how you go about factoring it. You have to set your factors equal to 0. Divide by 4, that literally does nothing, so 0. Add the 1, divide by 4, you get 1/4. I don't mean to be that guy, but what is a real-world use of this process? Many real-life things can be represented by quadratic functions, like the path of a ball, the speed of a car, gravity, stuff like that. Lots of stuff in physics. So if you're trying to solve for the maximum speed, if you're trying to solve for when will the speed reach a specific speed, right? Any type of equation that you're solving in physics, if that thing happens to be representable by a quadratic function, this is how you solve that function. For real. So one more time, looking at this guy, what is the GCF? What do they both have in common? They both have an x in common. That's it, right? There's a 1 right there, but I don't need to worry about that. So they both have an x in common, so I yank that out and I'm left with x plus 10. So sort of like what happened over here, right? Over here. All they had was an x in common. So what are my two solutions? X equals 0 and x equals negative 10. Again, I'm trying to make a good habit for you guys. Please list them in order of small to big. Okay, it's just a good habit to form. Thank you. That does not look like a 10. That looks like gibberish. So the method that, 10%. Oh, crap. Okay. The method that I showed here would and still works. But there's just some tricks here when a function takes up a specific form, right? The messier it gets, the more likely you're going to use the method that I taught you last time. But the simpler it gets, right? These only have two terms. The less likely you're going to use this because there's just probably something quicker, right? This works every time, but sometimes there's just something a little bit quicker. I love the fadeaway circle. Thank you for noticing that. It's my favorite thing about this app. Solve a quadratic equation by factoring. So we need to solve this by factoring. All of these were set equal to 0. We had a few problems last class that weren't set equal to 0. And what did I say? I said set it equal to 0. Okay, let's do that. The speed of a rocket ship is represented by 25x squared equals 16. The speed of a rocket ship is represented by 25x squared. When will the speed of the rocket ship reach a speed of 16 miles per hour? We're solving that, right? Now, I know that a rocket ship wouldn't be that simple, but you get my point. I just messed that up. Minus 16 equals 0. And voila! Again, we're back to this easy thing. When you see perfect squares, 25 and 16, that's not a coincidence, okay? That is not a coincidence. Chances are your eyeballs need to be open and you need to be like, yo, perfect squares, subtraction, it's a difference of squares. I'm going to use that nice easy pattern that Mr. Skis taught me. Take the square root, take the square root. So 5x minus 4, 5x plus 4 equals 0. And our two solutions are 4/5 and -4/5. Probably most of you are like, I'm literally not going to write out this other one because every single time it's plus or minus. Yeah, it is plus or minus. But I'm just proving a point here, or I'm stressing the point, not proving, stressing the point that how do you get our final solutions? You set the factor, because we factored it. That's what this is. I can't stress that enough. The skill of factoring is something that's important. And once it's factored, we just set the factors equal to 0. Okay? Are we done already? Wait, did something get caught off these notes? Do you allow the use of the plus or minus answer? I yeah, that's fine. Because everything's students in general watching the replay, if you're used to that plus or minus notation, that's fine too. However, as we type our answers on an online platform like Canvas that we use to submit our answers, there's no plus or minus button on a keyboard, right? We're not physically capable of typing that button. So for the sake of Canvas and for the sake of answering these questions online, this is the route we kind of have to take. Classy memes. Thanks for following. You're still here watching. I appreciate you. Did my notes get cut off, or is that really all we had planned for today? COVID rumor. Well, that's the end of the notes, but I think, if you're still watching, you're watching the replay person, and you're like, I want to see one more, maybe two more. Let's just do that. Let's do that real quick, okay? Let's do one more for good measure, all right? So let's say I have 16x cubed minus 6x squared equals negative 10x squared. Let's do it. You are cubed. All right. 16x cubed minus 6x squared equals negative 10x squared. Well, you might look at this and go, well, we haven't seen cubed even once in this class. You're right. We haven't seen cubed in this class. But that doesn't make a difference. Let's just set it equal to 0 and see what happens, okay? You might look at that and be a little worried, but let's set it equal to 0 and see what happens. 16x cubed minus 4x plus negative 6 plus 10 is plus 4x squared equals 0. All right, so I see the perfect squares 16 and 4. However, I also noticed that they have x's, which is different than what we have seen, right? 25x squared minus 16. It was just a number. Just a number. Okay, so what's the deal with that? Well, let's try to take care of business here. What's the other thing that we learned in this lesson? Greatest common factor. What do they have in common? They're both divisible by 4. and they both have, this is 3 x's, and this has 2. They both have 2. So how would I write that? 4x squared. So I'm going to yank a 4 out of this, and I'm left with a 4. I'm taking out 2 x's, so I'm going to be left with 1. And then I'm taking away everything. And often students are tempted to write 0, but no, there's still a 1 left over. Because remember, you got to be able to put this back together, right? You got to, we're disassembling it, factoring it. We're disassembling it. And you got to remember, though, that you should logically be able to put it back together, right? If you can go this way, you should be able to go this way. So if you just had 4 times 0, that would just disappear. So that's not right. There needs to be a 1 there. So voila. I'm factored, right? There's nothing else to do. You realize that, right? We got rid of the perfect squares. So this is 4x squared equals 0. That's factor number 1. And this is 4x plus 1 equals 0. Divide by 4, I'm still left with 0. Take the square root, I'm still left with 0. Subtract the 1, divide the 4, negative 1/4. So there's a little bit of tease, right? There's a little bit of tease there of a perfect square. I just came up with that on the spot, people. That's how skilled I am. So a little bit of tease of the perfect square, but then when we took the GCF out, we were all good. If you're still watching me, replay or otherwise, something that I think is worth noting, check, or you know what, let me put the word always. Always, red? Yeah. Always check for a GCF first. Always, right? Because number one, that's the easiest thing to do, right? To look at 3 or 2 numbers and go, what do they have in common, right? Take care of that first. That's got to be the most obvious part. And then once you've taken out the GCF, what's left should be easier to handle, and you might be done in the situation of this problem. We were just done. But sometimes you might be left with something that, you might look at it one way and go, this looks hard. Take out the GCF and you're like, oh, this is easy. And with that last example, I think we're good. If you're still watching me, I know I keep saying that, but if you're still watching me and you're curious, the homework will be a mixture of problems, right? A mixture of problems. So the good old factoring from the previous lesson is not just out the window, right? We need to still be able to do that. And then these guys are more like the easier ones. Like sometimes this neat pattern shows up and sometimes this neat thing shows up. And we need to be able to handle those and recognize how easy they are amongst the harder ones that take a minute, right? Like my first example, right? That was probably the hardest one I did. And that was the one I just made up. I feel like a perfect square is a GCF sorta. Is that accurate? Well, these perfect squares, 16 and 9, do not have a GCF. Which is why I immediately just factored like this. I didn't even ask the question of what do they have in common. Can I do example 1 again? Yeah. Like the whole thing? Actually, let me not erase and let me just rewrite the problem. X squared minus 25 equals 0. So I did all of these examples over here on the right, where I was drilling in our head that when you have 4x minus 3 and 4x plus 3, the middle terms are going to cancel out, and you're just left with 16x squared minus 9. Perfect squares, because this thing times this thing is what generated the 16 in the first place, and this times this is what generated the 9, right? So of course it's going to be a perfect square. 5 times 5 gives me 25. 2 times 2 gets me 4. Perfect squares. And the middle term canceled because 5x plus 2, 5x minus 2. The plus and the minus force these two things to cancel out. 3x minus 4, 3x plus 4. I end up with my perfect squares because 3 times 3 and 4 times 4, and the middle terms are canceling out. So when you have a plus and a minus, it always results in no middle term. So when I look at this and I'm like, how do I split it up? How do I factor it? Well, I know that those factors got to be a plus and a minus, right? Because there's no middle term. So I look at this and I go, these are perfect squares. X plus 5 and x minus 5. X times x gets me x squared. 5 times negative 5 gets me negative 25. Right? I'm just doing this in reverse. So I look at the next one. 16x squared minus 4x. Or 16x squared minus 9. That was example 2. 16x squared minus 9 equals 0. So again, I'm doing this in reverse. So I know it's a plus and I know it's a minus. Well, 4x times 4x gets me 16x squared. And 3 times negative 3 gets me negative 9. And that middle term is going to cancel out because of the plus 3, minus 3. Again, doing this logic over here in reverse. And the last one, 4x squared minus 81. Pretty sure I had a 2. Oh, shoot, I did have 2. Oh. Man. I'm dumb. For x squared. You trusted me. Don't trust me. I can make a mistake every once in a while. Take the square root, take the square root. 2x minus 9. 2x plus 9. Slow Turner, you feel good about that? Oh, this is a good Harris beat right here. A little. Would you like to? I don't know either. I mean, I can literally just make up a million examples. I didn't solve these, by the way. Should I have solved them? I just factored them. Right? This gives me a solution of negative 5 and positive 5. This gives me a solution of negative 3/4 and positive 3/4. This gives me a solution of 9/2 and negative 9/2. But I look at these two numbers and I'm like, hey, they're perfect squares. Take the square root, take the square root, plus or minus. You got a big delay, Slow Turner. Not a big delay, but a little delay. So I immediately know 5x minus 6, 5x plus 6. And how do I solve these? I'll solve this one a little bit slower. Set your factor equal to 0. Cube. These types of problems are like, would probably be 50% of your pre-test to see which class you would get in, and I'm not even joking about that. Like, there would be so many problems like this. Like, solving quadratics. These are easier, but, like, solving quadratics in general. So, like I said, I can make up a million of these. Why do I know that it's so easy to factor like this? Because it's a difference of squares. Difference meaning subtraction, squares referring to perfect squares. So I look at this and immediately I'm like, yo, that's a perfect square. That's 7 squared. Whoa, that's a perfect square. 2 squared is 4. So I immediately know this factors into 7x minus 2, 7x plus 2. Because I'm taking the square root. And then I set these factors equal to 0. And I get 2/7. And I set this one equal to 0. And I get negative 2/7. Yeah, Slow Turner, if you got a follow-up question, let me know. Yeah, I have this stuff down fairly easy, but my issue comes from question phrasing. You can have x squared minus 25 equals 0, but they're looking for you to solve something else. No, they're not. They're really not. If it says solve for x, right, no matter how they phrase it, now they might be like solve for x using this method. If they're going to look at your work, then yes, you would need to know the method that they are requesting you to use, right? Because you can solve that problem many number of, but I highly doubt they're looking at your work, right? Because that pretest is probably multiple choice, right? I would assume. But I mean, they might give you this problem and you could solve it like this, and then just take the square root. Or you could look at it and say, I'm gonna factor it. Right? I mean, boom. Just 2 things right off the dome that you could do. What's this banner? Alright. Could you do another example similar to example 3? For sure. So example 3 is literally the same thing. Oh, is this the one you were referring to? This one is called matcha. All right, Slow Turner, we have 5% left. So any of these problems, right? So how am I just coming up with these problems on the spot? Because I know perfect squares, right? 5 squared, 6 squared, 7 squared, 8 squared. So 64x squared minus 16 equals 0. Okay, that's when it's equal to 0. Example 3, what was the only difference from example 3? It wasn't set equal to 0. That was the only difference, right? It's way up here. That's the only difference, is that it's not set equal to 0. So by simply setting it equal to 0, I'm looking at a problem that's the same as the previous 3 I just did. I go, whoa, I'm set equal to 0. I have a difference of squares, difference meaning subtraction, squares meaning perfect squares, and I'm like, all right, 8x minus 4, 8x plus 4 equals. So I set my 2 factors equal to 0. When I divide by 8, 4/8 is just a half, and I hope you've at least caught up on the rhythm that the other one will be negative a half. It's off his Skura Dreams set. I just play that playlist, so. Are your answers set up to expect simplification, or would 4/8 still be acceptable? No, I expect kids to reduce. If a kid falls victim to typing the wrong thing and they get marked right or wrong, I'll give them the points and I'll be like, I won't do this for you next time, right? If they message like, hey, I had 4/8 instead of a half, I'll be like, I'll give it to you this time, but you need to reduce because I'm not gonna mark this. I'm not gonna manually change your score every free. Because the point is it gets auto graded to a half, and I have to go out of my way to mark 4/8 correct. So no problem, Slow Turner. I appreciate you watching. This is exactly why students should tune in live, because you are able to ask a question and ask for more of an example. If you have friends in class, Slow Turner, tell them to watch, because they need to. You need to be the guy or the girl. I have no idea. Wait, I've been calling you Turner, and it says Towner. I am so dumb. I thought that was... Why did I say Turner? What? You do. Well, I appreciate you trying. I have no... I think I just misread it one time, Slow Turner, because I've called you that before, haven't I? I think I misread it once, and my brain's like, oh, I know that username. It's Slow Turner, and then my brain's just automatically autofilled, and now I'm looking at it closer one more time, and I'm like, that doesn't say Turner. That's so... Oh man, that's so funny. I've said that like multiple... No, yeah, I've said that like multiple times. Like multiple streams. My brain has just been on autofill. That is so funny. I hope I didn't insult you too much by reading your username wrong. Oh man. You're tutoring for free. It's not something everyone has access to. What isn't? Twitch? Are you implying people don't have access to Twitch? Yes, they do. Every single student is expected to have. Yeah. Oh, okay. No, I need to do more with and make like kind of snippet YouTube videos, but the thing is it just takes time, right? Like, you know, I've got my own class to manage, and when the day's over, I'm just like, okay, I'm gonna make sure grades are good, prep this for next class, and then I'm done. So if you go Slow Turner, Slow Towner, if you go, if you're on a computer, if you're looking at my stream, you got the chat to the right, and you click the settings gear under chat. No. Wait. There's a way to view... Where's that setting? You're on a phone. Cube, is there a way to adjust the stream delay on a phone? Is that like an option? Watching on a phone? There should be, like, in the settings gear, it says, like, opt for something about choosing to watch on less of a delay. Literally getting an ad for my own stream. So in the settings gear, when you click on the stream, once my ad ends, you click the settings gear and it says, I'm not seeing anything. Chat only, audio only, enable filtering in chat, readable colors, background audio. Is it within the settings gear of the entire app, maybe? If you click your profile photo, slow counter, you go to account settings, maybe? Preferences. Nope. Security and privacy? Probably not, but I'm gonna click anyway. Nope. System? Nope. Recommendations? Nope. Potentially, if you go on a computer and set it up on the computer, it might apply those same settings to your phone. Even though we can't seem to access it from the phone, it might apply the settings despite the fact that that's all I got. That to me sounds like it should work. Because I just pulled up my own stream and I was like looking, I was practically seeing it in real time. I could tell. So my phone, and I'm logged in on a different account, right? I'm not logged. It's not like I'm logged into my own. I'm logged into my personal account on my phone. So if that makes sense. You can also try refreshing. Sometimes if you lag behind a couple of times, it will add up. That's true. Even if it buffered once, twice, 3 times, that's 3 seconds there, 3 seconds there, 3 seconds there. All of a sudden, you're not. All right. Well, thanks again, Slow Towner, and thanks Cube for hanging out. Are we? You wanting to play anything? What are you doing right now? Or are you about to go to work? I should probably go to just chatting, so I'm not all teeny. Do you, bro? I did say it right. You really want to play No Man's? That was like so weird. Is that really what Minecraft is like? Thank gosh I never tried playing Minecraft. I believe that. It seemed like there was so much maintenance. Like, I felt like my death was impending too quickly. See a Slow Towner? I feel like my death was like... It was like they were trying to simulate time passing, but like... It was just going by too quickly. And we were playing for like an hour, and my health depleted like 4 times. You telling me my freaking oxygen tank can't even last 15 minutes? Pretty sure I can scuba dive for an hour. Well, what they're gonna do is they're gonna make me think I need to freaking hoard O2 and sodium, and then I'm gonna run out of room in my backpack or whatever they called it, right? Like, there's probably a maximum capacity to what you can hold, so I'm gonna. And then it's gonna be like, well, what do I get rid of? Do I get rid of the sodium or do I get rid of the platinum? Gotcha. I could upgrade to an oxygen tank that doesn't run out in 10 seconds. Alright. I'm for reals ending it. So that way I can post the replay here in a little bit. Alright. Where's my class has ended scene? Deuces.